good lunch. Actually, the course that I usually teach at McGill always seems to be at 1 o'clock in the afternoon. So I'm used to having large classes of students who are sort of well satisfied and half falling asleep, but hopefully I can keep you awake. Hopefully all that food's going to your brain, and so you'll be aware and conscious of what I'm talking about. But what I want to talk about in this lecture is to talk about three things which are linked, I believe. One is, the main thing is attention, and then there's words that we've already heard in this conference, doing and feeling. So doing action, doing things, which is very important for robotics, of course, feeling or consciousness or all those other words that Stephen listed this morning. And what I want to do is talk about attention and how it links between these two. First, I'm going to talk about link between attention and consciousness, or feeling. Then I'll talk about link between doing and attention, or attention and doing. There's some interesting links between that. And then finally, talk about link between doing and feeling. And all these are interconnected, and perhaps it's important to understand these links if we want to understand how humans can feel, or how even robots could potentially feel. So let's begin with the first, just a quick overview of what attention is. Most of you are probably familiar with the concept of attention. It's a rather vague concept, although a roboticist or machine vision person would have a somewhat more concrete definition. But I'll take the one that's on Scholarpedia. It says, refers to the process by which organisms select a subset of available information upon which to focus for enhanced processing and integration. And attention is very useful for organisms, and presumably for robots, in that it permits rather complex processing and analysis of sensory data to be performed with limited computational processes. And this is very important for robotics. So in the types of robots that Yanis talked about earlier, you don't want to have to carry around a massive computer, so forth. You have a limited amount of processing that you can do in a given amount of time, limited amount of memory that you can store, and so forth. So it'd be good if we can have some sort of processes that would whittle down the amount of information you have to process in a given time to carry out a given action. And so attention is something that allows you to do that. It focuses on a subset of the massive amount of information that's potentially available, just onto information that is relevant to the task at hand. So that's what we're going to consider as attention. And I'm not going to talk about the ways in which the brain or machine systems can actually implement attention. We're just going to look at the high-level thing. And so attention processes have been studied for a long time, probably even before the time of William James and Helmholtz, although they're probably the first to treat it sort of as a scientific endeavor. And since their time, there's been a lot of work and a lot of very good science that's been done looking at the purpose and structure of attention processes, mostly looking at the selective nature, that is, selecting out a certain subset of data that you want to process. So what I want to talk about right now is look a little bit at the link between attention and feeling, or attention and consciousness. Okay, now, this is a very big area. We could have a whole symposium just on this. So I'm just going to try to give you a flavor of this so you get some idea of some of the issues. Now, one way to look at it is that as I look around, I see a very rich world. I see lots of different colors, I see lots of different faces, people, and so forth. And it's our impression that we're continuously registering every detail in the scene before us. But in truth, we actually see very little at any given time. If you start doing psychophysical studies of what people are actually aware of, or information that they've actually captured, it can be quite a small amount. I'm not going to go through all the psychophysical studies that show this. There's plenty out there for you to read in the literature. But one view, or actually a number of views, have this sort of form. Again, I took this from a nice write-up by Lawrence Ward on attention. You have the upper diagram. It's a simple model of link between attention and consciousness, where you have some processes that select out various inputs and you have some that you attend to and others that you're unattended to. And the inputs that you attend to get passed through some box here that's called conscious, which allows you to make a conscious report. Okay, so if you ask me, who's in the front row, I see 3 people. That's a conscious report of what I'm aware of. Presumably that involved attending to the front row and doing some sort of search and counting operations. Okay, and notice in the top diagram that the only aspects of the input that you can actually make a conscious report of in this model are ones that you attended to. Now, there are other models which turn this around a little bit and say, well, some things you're conscious of, you can attend to or not attend to, and the things that you attend to, you can make a report on. But I prefer the upper one, and that's the one I'm going to sort of take as our straw man for the rest of this talk. And so the idea of this very simple schematic is that what we're conscious of is what we attend to. And one thing which points at this is a set of experiments that I did with my colleagues Ron Rensink and Kevin O'Regan. We were both, for a time, working at the Nissan Cambridge Basic Research Center, which was a research center that only lasted about 5 years, but was rather an interesting one, funded by the car company Nissan. And they wanted to look at cognitive processes involved in people who are driving, okay, to try and basically improve the driving experience. That's what they're after. So there's a number of studies done there, but one was studying what came to be known as change blindness. And so in these experiments that we ran, people would be presented with video sequences of scenes containing large and clearly visible changes, but these changes would be nevertheless very difficult to detect. And the idea is basically that we present an image of some scene, like the scene in this room, and then we have just a blank image where nothing is displayed. It's just a white screen. And then we present the image again with some changes made in it. For example, we might have, if I'm looking at the scene here, one of the people may disappear, or they may move, or their color of their shirt may change from red to green, and so forth. So we have this sort of change. And with this type of presentation, it was found that it was very difficult for people to notice these sorts of changes because of this intervening flash. So here's an example of one. I hope it shows on this screen. The timing is perhaps a little strange, but there's a rather large change going on in this image. So there's an alternation. We show up an image, and then there's an intervening blank screen, and then there's another image, and there's a change going on in the screen. Okay. Now this one, the change. How many people can see the change? Okay. So quite a few. How many saw it immediately? Okay, not so many. So the change is that in the right-hand side here, there's some background sort of going and disappearing. They may say, well, that's cheating because, nobody looks at that part of the image. It's not interesting. But that's actually a key point. It's not interesting, and so we don't pay attention to it. Another example, this one is perhaps, it's probably the same sort of difficulty, but the change is perhaps a little more salient. Okay, so again, it's the same thing. We present an image, then we have intervening blank screen, and then another image where we have some change in the scene. In this particular one, the change is that there's a bar in the background which is going up and down. Okay, so it's when we ran the experiments on this, we had a whole set of different types of images. We ran on, I think, for original experiment it was 10 people, and so forth, and we just measured how many iterations or repetitions it took for people to recognize the nature of the change. And we also measured the eye fixations of people when they're doing this. And it was interesting. So in this previous image, the task was that people had to detect the change and report the nature of the change. So in spite of this, when people looked at these images, they tend to focus on the same things all the time, okay, or fixate. They typically look at faces, they look at the hands, they look at sort of the food, the wine bottle, the occasional sly glance to the, to the neckline. But only once did this particular trial actually look at the bar that was changing. And presumably that's could be when they would say that, yes, there's a change going on. So even though they're supposed to be looking around the whole screen and whole scene, and if you talk to these people, they say, yeah, I'm looking over the whole screen. I'm trying to see what's going on. Actually, they're fixating on very stereotyped things. Now, the results were interesting. Here is shown the number of repetitions or alternations it took before it was recognized that there was a change or what the change was. And these image alternations occurred about once per second or 1.5 times per second. The average number of alterations detected for changes that what we called central interest, which were things like, the faces and the food and the wine bottle, were 7.3 alternations. So it had to flash 7 times before people, on average, where people would detect this change. But if the change occurred, say, like, for example, in this bar, which would be a non-center of interest because people normally don't fixate on it, then the detection time would be quite a bit longer. It takes 17 alterations. And how we define the notion of center of interest or non-center of interest is that we had a separate population of people that would look at these images and describe them. So, for example, if you describe this image, you would say, well, there's 2 people sitting at a table, eating dinner, and there's a wine bottle, and there's maybe some fields in the background. That might be the description. So things that they mentioned would be center of interest. Things that they didn't mention would be non-center of interest. And I don't think anybody ever mentioned the bar in the back. So that would be a non-center of interest. And so we see that it took longer for people to detect the change when it was to something that you weren't normally paying attention to. But even things that you were normally paying attention to also took a fairly long time to detect. Now you see this, there's sort of a gray bar down at the bottom. That's actually the detection time when there was no intervening blank screen. Okay, if you just showed these 2 images consecutively, the change pops out immediately and everyone can see it within 1 alteration. It's only when you put in this intervening flash does it now become difficult to detect the change. Okay, and so there could be a number of explanations for that. The one that we take is that attention or detection of change requires attending to the change and then analyzing the nature of the change. And if you disrupt attention, say by putting this flash in, it delocalizes you're not able to localize the locus of the change, and therefore you're not able to analyze it. There are other disruptions, however, that you can apply. For example, and actually where we started when doing this study, is that if you do the change during a stochastic eye movement, then it's very hard to see the change as well. This was actually done by a fellow named John Grimes, University of Illinois, before we did our study. And actually it was the motivation for doing our study. We're trying to understand what's going on. Also mud splashes, which I'll give you an example of in a moment, which is basically not, instead of a large blank screen, we have isolated little distractors. Also eye blinks. When you blink your eye, we change the picture, then it's also very hard to detect. So there's a number of disruptions of the visual input that can cause these change blindness. Now here's just an example of the mud splashes. Since we were working for the car company, we thought we'd do one with a car and driving. It actually can be important for driving. If you're driving along and the car ahead of you puts on its brake lights and you don't notice it, you might plow into the back of them. Okay, and there's all sorts of these issues about attention while driving, as you're probably fairly well aware. So what's happening here is that these little spots show up in the image, and when they occur, the change in the image occurs. So there's a fairly large and actually salient change occurring in this image, and it typically takes people quite a long time to actually determine it. So the change is, if you haven't seen it already, it's this dotted a white line here, changing from solid to a dashed line, which I guess is important. If you want to change lanes, you can only do so if it's dashed, right? So this is just, again, a summary of the results for this mud splash. If you look at the left-hand column of the data, the right hand is for a slightly different experiment. You notice that there's a difference between central interest and non-central interest, or what we call marginal. You're faster to detect central changes, but you're still fairly slow. You can see, for example, in the case of where you have objects appearing or disappearing, which this previous example was an example of, 40% of the time people get it right the first time if it's a central change. But many times you get a significant number who it can go at least 8 times and they still don't detect it. In fact, there were some situations where people could stay a whole minute. That was the cutoff, and they still haven't got it. Okay, so this is and this result's been replicated many times, and so it's very clear that if we disrupt attention, there are changes in the scene that we're really not aware of. This is just another thing where we actually did the blink experiment, where there's the only intervening disruption is the blink, and we make the image change during the blink. Then it's also very difficult. Now, what's shown here is just a diagram where it's the distance from the change, okay, from the fixation point. So your eye is fixated at a certain location, and we make a change to an object at a certain distance away from fixation. So if the distance is fairly large away, 10 degrees of visual angle, then the probability of detecting a change is about 1 in 10, where it means you get about 10 alterations or 10 blinks. Even when it's right at the location, if it's 0 degrees, so you're actually looking right at the place where the change is occurring, 60% or 40% of the time you actually don't see this change, okay, which is quite striking. And I actually took part in this experiment. We had basically have an eye tracker which detects your blink, and when I took part in the experiment, we actually used a large projector like this, and we had the person just sitting in front, and people will be laughing because they see this change, and the poor person with the eye tracker on can't see anything. It's very unnerving. Okay. So just to summarize this role of attention in this change blindness, the idea is that the spatial attention is thought to play a pivotal role in detection of change. And the idea is that we can detect change only if one can shift attention to the location of the change and then see that the change is occurring. And typically, the way this usually works is that if there's a transient or something that is changing, this creates a visual transient which attracts your attention to that location. And these such transients are actually very good at capturing attention. And then you can subsequently recognize the nature of the change. But if you delocalize this transient, such as having a flash or a blink or a saccadic motion, then at best you can say, well, something's happened. We had this big flash, but I don't know where the change occurred. So then you have to do a serial search through the image, okay, which goes back to that eye track that we saw with the image of the people having dinner. Then we have to search for the location and have to store in memory, what the thing looked like before in the previous frame. And that's a much longer process. And a harder process, it's not so automatic. Okay, so just to summarize this part, this is overly simplified, but gives you the flavor. The link between attention and feeling is that we're conscious of or feel only that which we attend to. Okay, now some may argue with that, but I think there's a lot of evidence for this being true at some level. So just keep that as your mind. So the next part I want to get at is the link between attention and doing. Okay, so again, we're looking at attention. We want to see, is there a link between doing things and attention? Now, this may be a little less obvious to people. The link between attention and consciousness might be more obvious to people that, if we're attending to something, then we're going to be more aware of it. But there's actually a very interesting link between doing things and attention. And part of this comes from looking at well, perhaps simpler systems, such as frogs and so forth. And in fact, there's an idea that visual attention mechanisms, if you look in the brain, may have evolved from systems that select targets for motor actions, such as we see here with the frog. Okay, it has a targeting system locating moving objects, which it can then go and grab with its nice sticky tongue, and then it's happy. Okay, and although this idea has not really been explicated too many places in the literature, one place where it is this work by Hikusaka and some Japanese people who talk about this. Okay, but actually there's been a lot of work recently, say since the mid-70s, early 80s, of theories of attention which have developed, which link attention with generation and control of motor actions. And I just want to talk about some of the more influential ideas. And it's been sort of a development over time, which is ongoing. There's something called ocular motor readiness models, which perhaps started from Bill Wirtz in '76, who proposed that attention shifts were programs for saccadic eye movements. Now, if you read the literature on saccadic eye movements and so forth, you read a lot, especially in the 80s and so forth, of what's called saccadic programming, okay, where you have a part of your brain which is trying to work out what's necessary to create a saccadic movement to a certain target. So these were programs. And Wirtz's and Muller's idea was that attention shifts are basically themselves a program for generating a subsequent saccadic eye movement. And then Klein called this an ocular motor readiness theory in trying to explain how attention would be related to this. And he said, when attention to a location is desired, the observer prepares to make a movement to that location. The ocular motor readiness has an effect of enhancing processing. So the idea is that if you're making a plan for some sort of motion, you're applying more neural circuitry to that target area and so forth, and that itself will act like an attention process because you're sort of giving more resources to developing this plan. So this was the ocular motor readiness models. But perhaps I think the nicest explication of this type of approach is the premotor model of attention proposed by Rizzolatti and his colleagues. And his first, I think, paper was in '83, although probably a more well-read one was this lower one in '87. Rizzolatti, by the way, is, for those of you who know about mirror neurons, he was the one who came up with this idea of mirror neurons. But before that, he actually had this rather influential model of attention. And it's a type of extreme form of the ocular motor readiness model, which encompasses all motor systems, not just the saccadic movements, but also arm movements and so forth. And this model holds that the systems which control action are the same as those which control attention. Okay, so it's a very strong statement saying that basically the attention processes are the same as motor processes. And here's a couple quotes from the paper from his group. The first one says, the mechanism responsible for spatial attentions are localized in the spatial pragmatic maps. And by spatial pragmatic maps, he means motor maps. Okay, and there's no such things as selective attention circuit defined as anatomical entities separated from the spatial maps. Okay, so they're like two sides of a coin, and you really can't separate them out. And another quote, this pattern of results supports the notions that spatial attention depends on activation of the same sensorimotor circuits that program actions in space. Okay, so I want to talk about, just to fix ideas a little bit, just about eye movements and attention from the premotor approach. Now, one thing which you realize when you start looking at attention and eye movements is that your attention's not always focused or pointing where you're attending to, or where your eyes are fixated. So if I'm, say, looking at my screen, I can still attend to something away from that. Okay, maybe I can see somebody moving over here out of the corner of my eye. Okay, so eye fixation is not the whole story of visual attention. But we can actually, using this premotor idea, is think about even when we have our eyes fixed, we can be making plans to move our eyes somewhere else. Okay, and so while our eyes are fixated, we could be shifting attention, and in the premotor idea, each of these shifted attention is a plan for making some sort of action to that location. And that could be a subsequent eye movement, or it could actually be a pointing movement, or it could actually be a moving your body movement. And sort of corollary to this idea is that when you move your eyes, then they move to where you just shifted your attention. This is actually a very important corollary because this will affect your performance in carrying out various tasks. In fact, this is one of the strongest pieces of psychophysical evidence for this, is that you can show that you're more sensitive to various things when those are presented at the location of a planned target. Okay, for example, if you put some color discrimination objects, you're always going to do better in performing this discrimination task if they're positioned at a place where you're actually planning to make an eye movement. Okay, so this is very important that before you make an eye movement, your attention seems to shift to that location. Now, often this plan is not carried out. In fact, most of the time, when you're planning to make a saccade or shifting attention, your eye actually doesn't move there. Okay, so these plans can be suppressed. Otherwise, we'd be flailing around every time we shifted our attention under this model. Now, one thing I just want to say, an experiment that I'd done with one of my former PhD students was we had the idea that, perhaps this suppression would not be complete in all cases. Okay, and maybe you may get some spurious or subliminal sort of response, even so, because you're making this plan to make this motion, so maybe you're very excited and you want to actually make the plan, then some part of your frontal cortex saying, no, don't make that, stay where you are. You might sort of start going like this. And so we suggested that perhaps this is why microsaccades are generated. Now, microsaccades, for those of you who aren't familiar with them, are very small eye movements which are seen during fixation. So if I'm fixating an object, sometimes your eye would shift very slightly, okay, like a fraction of a degree of visual angle. And usually you don't notice these, but they often occur when your eyes are fixated. So our idea was, perhaps these microsaccades, which have been theorized to be noise, or there's a lot of different theories, or just drift, or some random motion of your eye muscles. But we thought, maybe this is just a suppressed command to move your eye due to an attention shift, okay? Because you don't want to move your eye for every attention shift. And so we did some experiments, and this just summarizes experiments. But the experiment was that a person was fixating, and then there was a number of stimuli which they had to attend to, but not fixate on. And they had to respond to, for example, maybe a color comparison. They had to press a button if the colors were the same or different, so forth. And we tracked people's eyes, and we looked for microsaccades during this task. And we then correlated these with the actual directions of the cues or of the stimulus. And so what's shown here in the upper left hand, there's a pair of histograms of the microsaccade directions, either left or right, depending on whether the stimulus was left or right. We see that there's a bias. The microsaccades tend to be in the direction of the stimulus in this sort of situation. And these microsaccades also seem to be linked. If you look in the lower left hand, are basically a set of occurrences of microsaccades over time. Okay, and the zero time is basically the start of the trial, okay, where a fixation mark appears. The red vertical dashed line is the appearance of the peripheral stimulus that they're supposed to respond to. And we see that in this diagram, there's a peak in the microsaccades with a certain time after the onset of this peripheral stimulus. And so we took this as evidence that the person is actually shifting attention to this location, which they need to do to carry out the task, and that this may be generating microsaccades after 150 milliseconds or so. Now, you may see that there's a lot of other microsaccades occurring after this initial peak. Now, what do those do? Now, they could just be noise, But our idea was that, well, every single microsaccade that occurs is due to an attention shift. Okay, remember, these are not just for a single trial. These are pooled over all trials. Okay, so you may get in one trial, you may get microsaccade here and here. Okay, and so we thought, well, if these other microsaccades were actually due to attention shifts, what would they do to? Because all we have in this experiment is a flash which occurs, and they have to shift their attention to. So what could these be? Well, we thought, well, maybe it has to do with the manual response, where they're actually pressing a button. Okay, because they had to press a button if the central fixation mark and the peripheral stimulus were the same color or different. And so what we did is, well, let's try to line up these occurrence graphs, not with the onset of the trial, but with the pressing of the button. So that's what we show here. This red line is basically when the button was pressed. And so you see that there's actually a relationship here that they tend to line up. And these are the ones that are sort of off in this tail. If you actually line it up with the pressing of the button, then there seems to be a connection. And so our hypothesis for this is that what these correspond to are a shift of attention back to the fixation mark, because we had to do this color comparison task. Okay, basically to check your answer before you press the button. Now, these peaks occur after the button is pressed, but that has to do with the saccadic latency. Okay, your attention shifts first, and then you make the eye movement. And there's always a latency of between 100 and 200 or 300 milliseconds. Okay, so this occurs after the button press. So we took this as an example of a link between attention shifts and actual actions. Okay, even though there was no overt action going on in this experiment, there still was this sort of subliminal action, which perhaps is a suppressed response. Now, this work was replicated is too strong a word. There's a group in Germany that basically did the study at the same time. We published within a couple of months of each other this work. And so after this, which was in the around 2000, there's been a lot of work on microsaccades exactly looking at the link between them and attention. But I just wanted to give you this just to give an example of the strong link between attention and action. Okay, and again, I give an overly simplified summary of this between doing and attention. It says we act only on what we attend to, or vice versa. Because if you take Rizzolatti's view, they're basically two sides of the coin. You really can't separate them together. We attend to what we act on, or we act on what we attend to. But they're very tightly coupled. And if you want to understand why this would be, you can think back to the example of the frog, okay, who's only interested in acting on things that it can attend to. Okay, and in the human brain, maybe it's more advanced, and maybe we've co-opted this process for doing more complex, abstract things as well. But at the very bottom, there's a strong link between attention and action. Okay, so I want to then now look at this third link between doing and feeling. So we talked about a link between attention and feeling, and a link between attention and doing. So indirectly, we have a link between doing and attention because we attend to what we do, or we do what we attend to, and we are conscious or feel what we attend to. So there's an obvious link between doing and feeling. But there's another link that I want to talk about between doing and feeling, which are the so-called sensorimotor theories of consciousness, such as that of Kevin O'Regan, the colleague I worked on the change blindness with. And I'm not going to go into too much detail on this. This is still very controversial, and others in this room are probably more qualified than I in talking about it. But I want to give you a feel for this. And one of the reasons that we might want to consider a sensorimotor approach is mentioned here by Kevin O'Regan in a recent paper he had, although you can read his new book, which came out, for a better explanation of some of this, is when we talk about feeling, or try to talk about feeling, one of the problems is that feelings are ineffable. We can't talk about them. Okay, it's sort of hard. But something that we can do is talk about the structure of feelings. We can do comparisons, for example, or we can do rankings. we can say one sound is louder than another, or we can say that yellow is closer to red than it is to blue, or things like that. So there seems to be a structure to our feelings. And maybe we can talk about structure. Now, many who talk about structure would look into the brain to try and see where the structure comes from. Okay, they look at neurons and neural states and so forth. But doing this is problematic. It hasn't stopped people from doing it, but it's problematic. And one of the problems is that, well, if we had a slightly different makeup to our neural processes, would our feelings be different, or would our structures be different? And it seems hard to actually pin things down when you try to look at the brain. But one approach to getting around this is to say, well, let's not worry about what's going on in the brain per se, or at least a particular structure of the brain, but try to see the structure of what it is we're trying to sense or what we're trying to feel. So looking more at the outside world than the inside of the brain. Okay, and so here we're talking about modeling structures based on external or world states, which can get around this problem. But then the question arises, well, how can the brain build and access such external models? Well, as a machine vision person, the idea to me would be, well, we should be looking for, what is the information in the sensory signal, which is allowing us to model what's out there in the world. And I like to use the example of color. Okay, so, what is it in the incoming sensory data that actually captures something that's in the world that tells us about color? And now philosophers have long argued about whether color is in the mind or whether it's something out there in the world. I like to take the view that it's out there in the world, but still say, well, how can we extract this information? Well, we can try to get to reveal or uncover invariants in the sensory data that captures something about what we're trying to sense, such as color or size or motion or so forth. And one way to do this is to use the sensorimotor loop. Okay, so if I move an object, okay, this induces a change in my retina, okay, which in some sense depends on the coding I have in my brain, but in a deeper sense has something to do with the laws of physics, okay, which you have this invariant object, you're assuming the object isn't changing itself, you're just moving it, you're inducing a change on your retina. There's some sort of laws which govern the nature of these changes. And it's the sensorimotor act which is actually revealing or uncovering these changes. So I just want to finish up by giving a rather interesting example of this, which is relates to a problem which is very fond in the hearts of many philosophers, which is looking at spectral inversion or inverted spectrum problem. And simply put, it's the problem of if I see a green object, do you see it as red? But we just both call it green. Okay, so that's the idea of the inverted spectrum. When I see red things, you see green things, but we both have agreed to give it the same name. Now, is that possible or not? Okay, and so again, philosophers, you can find people arguing on both sides of the problem. But in my view, or the people who take the sensorimotor view, say, well, it's actually impossible, or not. It's the wrong idea to think of sensory inversion, because really what you're trying to do is extract information that's out in the world, not in the head. If you take that view, then there is going to be some color. The physical approach would be the spectral reflectance or something like that, which is invariant, and as you're sensing it, you're trying to uncover that invariance. Okay, so here's an example of how this might work. So we have two people, one person with a normal brain, the other one with whose neurons have been scrambled so that their L channels from their long wavelength cones have been swapped with their medium wavelength cones. Okay, so for those of you who don't know about long and medium, think about having a computer monitor and swapping their red and green lines. Okay, so you'd have green turning into red and vice versa. Okay, so one view is if the color just depended on your internal state, is that they would have actually two different perceptions of the world. Okay, the normal brain would see things sort of vertically, and these element swap brain would see things differently. Now that would, that would mean that they would see the world differently. In our view, we want to see the world as it is, okay? So they should both see the same way. Now, I should point out that this is not just a sort of thought experiment. You can actually have people that have such swap L and M receptors, because color blindness is one way to get colorblind is there's a mutation that can happen which can basically convert L-type receptors into M-type receptors. And there's also another type of mutation which can basically convert M-type receptors into L-type receptors. Now, if you just have one of these mutations, then you have color blindness because you're just left with L and S receptors, or M and S receptors. And you lack one of the other ones, and so you just have a dichromatic perception. But sometimes you can actually have both mutations happening at the same time. So your L receptors have changed into M receptors, and your M receptors have changed into L receptors. But the end result is still the same, but now your wiring may be scrambled, as shown here. So in that case, those small population of people that have these sort of swap receptors, do they see things differently than people with the usual sorts of things? And so some of you who've read about the inverted spectrum problem may be aware of Ned Block's take on this, where he said, well, we could have an inverted Earth or a twin Earth, where this fellow got put into a world where the objects were painted, okay, so that they would have, colors which would map then to the same colors in the two worlds. So in this situation, the two people would be in different environments, but they would have the same mental states or the same perception, which is sort of a dual version of this. But perhaps is an easier way to understand how you might get around this. And so the way I want to show that this inverted spectrum may be a non-problem is to think about what actually happens in the world when you actually make eye movements or do other physical manipulations, by doing actions. And these are something which Kevin and Regan calls sensorimotor contingencies. Okay, it's sensing that depends on particular actions relative to color. So suppose we had these three color patches on the left, and we did an eye movement across the patches. Okay, so I'm looking at this red square, and I move my eye across it. So what happens when you move your eye across a patch? Well, some part of the patch is originally on your fovea, okay, or actually in the periphery of the corner of your eye, and then you're moving your eye so that now you're foveating the patch. Now, the real world comes into play here because the lens of your eye is not perfect. It's pretty good. It actually has some slight absorption of blue light. It's sort of slightly yellow. And actually, if you eat a lot of carrots, it gets even more yellow. Although your vision generally gets better, but it gets yellower. And that means that you have this color shift as you move across, as your eye moves across. And it depends on the actual color of the patch you're looking at, the effect of this eye movement. So when you look at a red patch, this yellowing actually causes very little change. If you have a green patch, it makes it a little bit yellow, greenish yellow. If you have a blue patch, it doesn't change the hue so much, but reduces the intensity. So you get something that's a little less. But the important thing is that you get this change between these two things. And so there's actually a contingency or a change across that. Now, if we look at our two people here with their normal brain and swap brain, and we assume that, well, they're actually looking at white patches. If we do the LM swap in the twin Earth, the painting, you don't have to do any painting. But when they're looking at the periphery, they both see sort of this white patch. But when they make the eye movement, they actually now see something different. Okay, which would be because they're actually in different worlds. And so the lesson to be taken home here is that the fact that we have these asymmetries induced by these eye movements allows us to get our perception back out in the world, because the asymmetries are something physical. They're not in the brain. Okay. Now another example of this is to do with interreflections, which is a physical asymmetry which is in the world, but also affects our perception. So here we have two color patches in the upper. We have a blue patch and a green patch. If we have these separated, one looks green, one looks blue. If we bring them together, now they reflect light onto each other. And since if you look at their spectrum, they actually overlap, okay? The green and blue have a somewhat overlapping spectrum. So you get some light coming from the green, which reflects onto the blue, which makes the corner bit or boundary a little bit sharper, or a little bit shinier. Whereas if you have in the twin Earth where you've repainted these things, you have a red patch and a blue patch, their spectrum are actually quite separated. So actually when you bring them together, there's very little interreflection. Okay, so the perception, again, is different. And it's different because you have this sensorimotor contingency. So just the final overall simplified summary, doing the feeling, we could say that the contents of our feeling depend on the way in which the sense data changes in response to the actions. Now, I think of these three items, the top one is probably the most controversial. Some people may question this. But nonetheless, I want to leave you with these three things, that there's links between doing, action, feeling. There's links between attention and feeling. There's links between attention and doing. And all of these, I think, go towards understanding how humans can feel, or how even machines can feel. And so there's implications for the Turing test. So one implication is, well, if a machine is to be indistinguishable from human, it should feel in the same way as humans. I think that is, if I understand correct, this is what Stephen is trying to get at with this workshop, is that trying to see if we can have robots feel the same way as humans. And if that's the case, then thinking machines should do planning of actions relevant to current situation, which is what they do. But they should also shift attention according to the plans in order to efficiently process the data. But also, they should proceed based on results of the actions, trying to search for invariants and so forth, which are out in the world, not in the head. I think that's an important aspect. And for the Turing test, the original one about imitation of humans, well, we could try to do robot psychophysics, for example. We could say, well, do robots actually exhibit change blindness? If they didn't, well, maybe they're not human. Or maybe they're just very attentive. But I think even very attentive humans would exhibit some sort of change blindness, and also exhibit linkages between actions and attention and so forth. Okay, so thank you for your attention.